So, in these two last lectures, I want to give you a general overview of the field of quantum information and give you one or two examples from each of the subfields so that you get a general flavor for what they are about. So, quantum technologies can be roughly divided into about 4 subfields. There is quantum sensing and metrology, quantum imaging, quantum computation and simulations, and quantum communication, which we've talked about lots and lots. So let's start with the first one. Quantum sensing and quantum metrology describe the use of strategies to achieve precision measurements which are beyond those available classically. And the parameter that we want to measure can be anything that you like, but two very important ones are the optical phase, so the optical path length, and the magnetic field. The optical phase is important because many things can be mapped onto it, and magnetic fields are interesting for the measurement of local environments from microscopy and so on and so forth. So let's have a look. So one big result which came out a couple of years ago now was the detection of gravitational waves. You might have seen this image floating around. It is an artist's impression, I guess, from NASA that described what was happening. So here you have two very massive stars coalescing, merging into one, and in the process emitting a lot of energy in the form of gravitational waves that is propagating through space. And this is the paper. And it's free on Physical Review Letters. If you're interested, please go read it. So I think people have been talking about detecting these waves for years and years, and we finally saw it. Well, how do we actually do it? So it turns out that when these gravitational waves propagate through space, and you have two arms of an interferometer that is orthogonal, it will stretch or compress one arm more than the other. So if we make these two parts perfectly equal, and then now the gravitational wave starts stretching and compressing one on the other, then there will be a difference in the path. The instrument that we use to measure these waves physically looks like this. So you have an interferometer, one path goes horizontally and the other one goes vertically. And this is an image of it from space. I think each of these arms is about 4 kilometers. Okay, so what this is schematically looks something like this. So you have a laser that is incident onto a beam splitter. So this is a 50-50 beam splitter. Half of the laser amplitude goes one way, it bounces back, and the other half of the amplitude goes that way and it bounces back. So I think it is designed such that all the laser power would come out of one arm due to constructive and destructive interference. And if there is a shift in the optical path due to these gravitational waves, then some of the laser power would come out of the other port, and that gets detected. And if you read the paper, in the abstract, it'll tell you that the signal sweeps upwards in frequency from 35 to 250 hertz. So that is 35 to 250 cycles per second, with a peak gravitational wave string of 1 times 10 to the negative 21. Now, pay attention to that particular number there. 1 times 10 to the negative 21. That means if you have something that is a meter long, the gravitational waves will stretch or compress one of them relative to the other by 1 part per 10 to the 21. That is a number that is very incredibly small, and the implementation of this particular measurement is, an incredible feat. That's why it's taken about a few decades, I think 40 or 50 years, and hundreds and hundreds of scientists working on them. So, and actually what we were when they first switched on the instrument, they weren't expecting to find that particular burst at all. Turns out that I think they were hoping that the sensitivity of the instrument will reach 1 times 10 to the negative 23. And when they first switched on, and so 10 to the minus 23 was where they were kind of expecting the signal to be in. And then we got very lucky that those bursts were so big that it was found pretty much as soon as it was switched on. And so, yeah, so that's one big victory of quantum metrology. But in fact, this is just a laser, and one could argue that this is not particularly quantum. So for the next upgrade for the LIGO interferometer, people want to put a squeeze state, which is a quantum state of light, into one port of the interferometer to boost the sensitivity, so that it becomes even more accurate. Okay. So now let's talk about quantum imaging. So if we talk about imaging, this is about taking a picture of something. And quantum imaging wants to image objects with a resolution or other criteria that is beyond what is possible in classical physics. So typically there are two ways of going about it. We can either do state optimization. So here we're allowed to illuminate the object, so we can shine things onto the target object. Or we can perform measurement optimization. And the measurement optimization is performed because sometimes you just can't shine light at your target. For example, if you have two distant stars, which are millions of light years away, then you have no control over the type of radiation that it is emitted. So if we're talking about state optimization, then typically we want to talk about reducing the inherent noise in an image, or we may want to perform target detection, or so quantum illumination is all about detecting a target embedded in a bright noise bath with higher probability of accurately determining the outcome than if you use anything classical. But okay, so let's talk about state optimization. So one topic which has attracted quite a bit of attention recently is ghost imaging. So here we want to use position and momentum correlated photon pairs to image an object. Say, for example, this skeleton object over here. So the scheme goes as follows. You have a photon pair emitted in this direction, and these are entangled. So we want to put a bucket detector behind the image. So this thing has no spatial resolution whatsoever. So all you get from the bucket detector is whether something arrived or whether something didn't arrive. So, and on the other side, so where you want to image, so on the other path, where the image is supposedly not there, you can put a screen. And because these photons are entangled, you can image the object by using photons which have never passed through the actual object, hence the name ghost imaging. So if you're interested in that particular scheme, it is given by this reference over there. And this is made possible because when the photon pair is created, when it goes through this object, we know that exactly another photon has gone onto the other path. And because these are position correlated, a photon that's traveled down this path, we know exactly where it will arrive on the other path as well. Hence, we can perform imaging with it. Okay. So that was an example of state optimization where you illuminate the target with a photon beam, an entangled photon beam. Now let's talk about measurement optimization. So this is exactly the example I was using before. You have two distant stars, which are both very faint, or very faint by the time it gets to your screen, your imaging screen. So something called the Rayleigh's criteria dictates that if you have a lens or an aperture with finite size, then a point source, so something at the distance that's a single point, will end up with a finite spread on your imaging screen. And the witness of your spread is inversely proportional to the size of your lens. So hence why, if you look at good cameras, they always have a very big lens. And if you're talking about those very large baseline telescopes used for astronomy, they try to make the lens as large as possible. So yeah, next time you go to a camera store, you know that you want to buy something that's big. So here, we want to solve the most basic problem of estimating the spread of 2-point sources. So how far these two stars are from each other. And on the image screen, they may look like that. Two approximately Gaussian point spread functions. And you can probably imagine that if these two get very close, then the two merge into one blob and you can't separate them anymore. And we call this the Rayleigh curse. Turns out that if you use a specialized measurement, even in the limit that these two become infinitely close together, or when the separation approaches 0, then you can still estimate this particular separation with a finite accuracy. And that is done by feeding what is on the image screen onto the Hermite Gaussian modes of a fiber, and then performing photon counting on those modes. And if you're interested in the details, that is given by this reference over here. So here we have a set quantum state emitted by the stars, and we're performing measurement optimization to do imaging, or super resolution imaging. That's beyond what you can do by doing simply doing photon counting on the screen. Okay, now let's talk about quantum computation. This is a huge subfield, And quantum computation seeks to perform tasks which have an advantage over classical computers. So when we say they have an advantage, it means that we're doing tasks which are either completely beyond the reach of classical computers, or these may be problems which are simply cheaper to do on a quantum computer. So cheaper means either time-wise or money-wise efficient. So if you want to solve a problem, so say for example, some things are doable, like technically doable on a classical computer, but if it takes a year, for a supercomputer to do, whereas it takes seconds for a quantum processor, then you might choose to use a quantum processor. And the main reason for the speed up provided by quantum computation is that the Hilbert size of your quantum system scales exponentially with the number of particles in the system. So if you're keeping track of exponentially many probability amplitudes, then you might want to use something that's inherently quantum. So you might have seen pictures like this of quantum computers floating around in literature and popular physics magazines. So actually, this is not a quantum computer. This is just a fridge that is making the actual quantum computer cold. So this is a multi-layered dilutionary refrigerator that's made of gold, because gold has very good conducting properties. And the actual computer, the actual quantum computer, quantum processor, is a very small chip that just sits on one of these, sits somewhere close to the bottom of these layers. So I suspect probably somewhere there. Okay, so we know that there are a few known useful algorithms which provide a speed up. Namely, we have Shor's algorithm, which can factorize large numbers in polynomial time, as opposed to what we suspect will take exponential time for classical computers. And also we have Grover's search algorithm, which can provide a quadratic speed up for searching and for an item. And very recently, because we don't have computers which have the capability, we don't have quantum computers which have the capabilities to implement these algorithms yet, scientists have turned their attention to problems which are known to have a quantum advantage or quantum speedup, but the problems may not necessarily but the task doesn't necessarily calculate something useful. So a couple of months ago, you may have seen news from Google saying they've achieved quantum supremacy. So that particular algorithm there implements. So that particular quantum processor there implements something called random circuit sampling. And that problem is known to be classically very difficult, but there is no actual known application so far. If we have these noisy devices, so what that does is basically you have a line of qubits, and you apply random single qubit or 2 qubit entangling gates, and because you have an exponential scaling with the probability amplitudes, to keep track of all those probability amplitudes is very memory exhaustive. So they did it on a 52 or 53 qubit chip. So if you do the numbers 2 to the power of 52 or 53, that took I think one of Google's major. That took one of Google's major storage clouds, And if you were to double the number of qubits, you need to double your memory again. So that we're saying, it's intractable. Or, if it took the most badass programmers and the biggest storage crowd to do, then it is not the problem that the average person can do, or the average person's computer can do, or even the average university supercomputer can do. So another problem that belongs to this category is boson sampling, if you've heard of it. So that's all about feeding single photons into an array of beam splitters which have certain properties. And that was actually the first time we have proof that quantum computers, so that was actually the first time that we have proof, rather than suspicion, that quantum computers can do something that's post-classical. And of course, later we found that these algorithms can potentially do cryptography, which is good news. So now let's talk about quantum simulation. And this is something that's actually potentially very useful in terms of economics, because Shor's algorithm talks about prime number factorization, and if we were to have a quantum computer now, it would actually be quite disastrous because that breaks our encryption system, and that would not necessarily bring about an economic advantage to the world, because the quantum simulation, on the other hand, is good for humanity. So why is that? So it became apparent in the 1980s that simulating quantum systems or molecules is a very difficult problem. And so Richard Feynman proposed, or in a very famous quote said that, let the computer itself be built of quantum mechanical elements which obey quantum mechanical laws. So the basic idea is that if something is quantum, then we want to simulate it using something that's quantum. So your quantum simulator can be any quantum system that you are able to manipulate. So you may have arrays of quantum dots. These are artificial quantum atoms that you make in semiconductors. You may have polar molecules, neutral atoms in optical lattices, trapped ions, cavities, nuclear spins, or superconducting circuits. So basically, whatever that you have access to that you can manipulate. So the basic idea is as follows. You have your quantum system of interest. So this may be your molecule or something that's happening in the Large Hadron Collider. You have a quantum state, and there is an interaction that you're interested in, and after the evolution, you have your final state. And let's say this particular quantum system you are interested in, but you don't necessarily have control over. So what you would do, you would take a quantum simulator that's prepared in some initial state. There is a unitary evolution that you can engineer, and there is a final state which you can measure. So the basic idea is that the simulator is designed such that there is a mapping between the simulator and the simulated system. So you have knowledge on the initial states. You can prepare an initial state in your simulator. You know something about the evolution from the quantum system, and you can engineer the evolution in your quantum simulator. And then you can't measure this quantum system that you want to simulate, but you can measure the quantum system in your simulator. So the result of the measurement on your simulator provides information about the simulated system. So that is quantum simulation in a nutshell. So what are some problems which are interesting for, or what are some of the applications? You have condensed matter physics. So because these are you have many particles, and these are many body problems. So these are typically very hard to do on a classical computer. So for example, we still don't understand the mechanisms for the high temperature superconductors. We understand the low temperature type 1 superconductor, but we don't really understand the type 2 ceramic type superconductors. So we want to gain some insights into exactly why they still superconduct at those temperatures. So these are 100 kelvins. You have high energy physics and cosmology. So once again, these may be events that happened at the Large Hadron Collider, or something that happens near a black hole. You have quantum chemistry. This is very important because apparently it's very difficult to compute molecular energies and molecular dynamics. So we may want to use quantum simulation to perform quantum chemistry so that we can gain some insights into chemical reactions and potentially help design pharmaceuticals. So you might know that designing a particular drug is very time and resource-wise expensive. So we have people who are physically trying to make drugs in the lab, but if we can use a quantum computer to help design these drugs, these may be very beneficial. And there's also quantum chaos and nuclear physics, which I won't talk too much about. Okay, so that was a very rough introduction to quantum technologies and what they're about. Now I want to come back and talk about some of the ways in which quantum key distributions can be, or quantum key distribution systems can be hacked. So we talked about before that classical cryptography assumes a bounded computational complexity. So we assume that a potential eavesdropper has bounded computational capacity, sorry, not complexity. So this is assuming that we're using functions or encryptions that could potentially cost the eavesdropper an infinite amount of time to hack, or years and years. So we assume that the eavesdropper does not have infinite computational power. And of course, this is a dangerous assumption once quantum computers come online. So if we want to do cryptography that is future-proof, we need to assume that Eve has an infinitely powerful quantum computer, and she can also perform arbitrary operations allowed by the laws of physics. Now, these sound like very stringent conditions, because if she can do anything, then we might be screwed. But however, we know that we have friends on our side. We have basically the known cloning theorem, and we know that measurement disturbs a quantum state. So in this context, the hacking of quantum key distribution systems actually exploit weaknesses in the physical implementation rather than the weaknesses in theory. So, so you produce a security proof on a system that you want to do QKD on, but what you end up building is always different from what you have proven on paper. So some of these weaknesses might be you have losses in the system. So your fibers and components are inherently not perfect. So if you send something through a fiber, you would expect that a couple of kilometers down the line, some of your signals might get absorbed. And if you send them through several hundred kilometers or 1,000 kilometers, it'll have absorbed a lot of your signal. So you have genuine lossy channels or components versus ideal ones where some of the signals have been tapped off by Eve. So it is not possible to distinguish channels which are genuinely lossy rather than a channel where you might imagine Eve has strategically tapped off some of your signals and taken it for herself. Okay, so you have imperfect components which might introduce errors in your final key. So in both of these cases, we need to assume the worst case scenario, that all the noise in the system is due to manipulation by Eve. So any errors that you see in your final key, we have to assume that they are due to the eavesdropper. So what a successful attack looks like. So a successful attack ends up with a non-negligible amount of mutual information with respect to the final secret key established between Alice and Bob, without alerting them that was taken by the eavesdropper. So if the eavesdropper is able to obtain a significant amount of key, or significant meaning not negative exponential, then she's considered successful. Okay. So let's talk about some of the ways, or some of the known hacking methods. So the security proofs for many discrete variable protocols assumes that Alice's signal consists of single photons. So this is the case for our BB84 protocol that we talked about, and some others. However, true single photon sources are not yet widely available, and QKD systems often use strongly attenuated laser pulses, and there is some probability that a source will emit multiple photons. So let's talk about the first part of this statement. True single photon sources are not yet widely available. So when we did our security proof, we saw that Alice emits a series of quantum states, and we assume that these are single photons, and when you measure it, it collapses the state onto whatever basis that she measures in. But however, we don't really have sources, single photon sources, which are press buttons. So you press a button and it shoots up a single photon, and deterministically. So why is that the case? It's because so for a laser pulse, the problem is that the distribution is Poissonian, and sometimes you get, so if you say I want my photon source to produce a state with mean photon number 1, sometimes you get 0, sometimes you get 2, sometimes you get 1, sometimes you get 3, and so on and so forth. So press button single photon sources are not yet available. There are candidates, but these are very bulky, and they usually need to be cooled at several Kelvin temperatures. So let's talk about the laser pulse. So you may have seen this particular representation on the photon number statistics of a laser pulse. So you have a laser pulse with probability amplitude alpha. So the mean photon number in the state is alpha squared. So it takes this form. You have e to the minus absolute value alpha squared on 2, and then summing over all the different probabilities of having n photons. So this is an n photon state. And the probability of getting an n photon state, given alpha being the amplitude, is e to the negative alpha squared, alpha to the 2n divided by n. Now, if we plot p and alpha on a graph with different mean photon numbers, we see that the blue is for alpha is equal to 0.1. I think the orange is for alpha is equal to 0.5. Oh, sorry, alpha squared is equal to 0.5. And then you have the green for alpha squared is equal to 1. So we see that, even if you use a very low mean photon number, you have a non-negligible chance of getting, higher photon numbers larger than 1. So what Eve can potentially do? She can potentially perform a photon number measurement on the signal to the states. Now she can steal the excessive photons and then send the rest to Bob. So a photon number measurement does not disturb, for example, the polarization of the state. So this is definitely allowed by physics. She can definitely steal them by, for example, putting them through a beam splitter and then keep some for herself. And now she's also allowed by physics to store the states in her quantum memory until the classical communication between Alice and Bob happens. So this is when, remember, this is when Alice and Bob exchange witch-basis information. And then hence now she can find out Alice's preparation basis. And now, she just takes her quantum state that she stored in the quantum memory and measures it in the correct basis, and she'll know exactly what Alice has sent. Now, this is a problem. We have a solution. The solution is called the decoy state method. So what Alice can do to counter this particular form of attack is that she can replace some of her signal states with multiphoton states. So these are our decoys. And because, remember, Eve is targeting states which have higher photon numbers. So now Eve cannot distinguish between decoy states and the encoding states. So she can so whatever she does to the high photon number states, she doesn't know whether it's a decoy state or a signal state. So she can only act identically on both the decoy and the signal so she can act only identically on both the decoy states and the encoding state. And in the post-processing stage, Alice publicly announces which states were the decoy pulses. So if Bob notices that the different photon number states now have been acted on differently, and they know that Eve is doing something in between, and they can choose to abort the protocol or try to catch eavesdropper. So in that case, she has not successfully stolen a large fraction of the key without alerting Alice and Bob. So the next attack we want to talk about is the Trojan horse attack. It is, as its name suggests, here Eve wants to send in some of her signals into Alice's preparation device in the hope that she'll collect some information. So here, Eve is probing the settings of Alice and Bob by sending light into the devices and collecting the reflecting signal. So Eve can send her own states into Alice's system, which will reflect off the same apparatus that Alice uses to encode her signals. So here, Eve is tapping into Alice's preparation device, so remember when Alice is alternating between the X and the Z bases, there is a physical device that is making that change. So here, if Eve states can be imprinted upon some information about the basis preparation used by Alice, when Eve measures these states that she sends into Alice's system, then she can retrieve information on the basis separation. She can retrieve information on the basis of preparation. Now, in combination with this measurement, so the measurement on Alice's, this measure, in combination with this measurement, which refers to Eve states, then in combination with operations on Alice's signal states, she can make a best guess on the quantum state that Alice sent to Bob. So this means, Eve has sent light into Alice's device. She retrieves her own states, then makes a best guess on Alice's preparation basis. And then in combination with this guess, she can measure Alice's state or perform some sort of operation on Alice's state. Now these are the states, the states from which they want to do key distribution with. So when combining those, she can make a best guess on what Alice's encoding states are, hence find out what Alice has sent to Bob. So if she knows what Alice has sent to Bob, she can definitely find out what the key is. Now that was an attack on Alice. On the other hand, Eve can also manipulate Bob's detectors and potentially force Bob's detectors to measure in the same basis. So what she does is that she can specially tailor light, a bright light pulse to send to Bob's detectors. Now she can trigger a detector whenever she chooses. And with a combination of these, she can manipulate Bob's basis choice of measurement. So remember, Bob has to choose randomly between the two, but this can be manipulated. Alternatively, she can also send in a very powerful laser pulse to optically damage the component in Bob's QKD systems and permanently change the characteristics. Because Alice and Bob both have QKD devices, right? If they don't know about the damage, and Eve has made use of that, then they don't necessarily know if that is the case, because your QKD systems are not necessarily equipped with alarm triggers. So this is a particularly nice paper that describes hacking commercial quantum cryptography systems by sending light into Bob's system. So this is the reference if you're interested in reading it. So so all of these methods that I've described are called side channel attacks because Eve is targeting something that we haven't considered in the security proof. So one of the long-term solutions to side channel attacks is based on entanglement. So here you want to distribute entanglement between Alice and Bob. And because the security of this protocol relies on the violation of a Bell's inequality. So that's just a number that can be exceeded if the system is actually quantum mechanical, so they need to share a maximally entangled state, rather than having a source that's emitting correlated photon pairs. So these may be correlated X states or correlated Z states. So if they can violate the Bell's inequality, they definitely know that the source is entangled. And if they're entangled, they can't have been manipulated by a third party. So basically, the security can be proven without knowledge of the actual physical implementation. So this is just, it's like having a QKD black box that emits certain states that have certain probabilities. And as long as you know the output, then you're safe. So cons, this entanglement-based QKD system or proposals have its own problems in the sense that the count rates are very low and it's much more difficult. So you might imagine it's not that difficult to send a train of laser pulses between Alice and Bob, and it has been implemented. It's been shown that it can work for several hundred kilometers, and it is so far very difficult to spew out entangled pairs for Alice and Bob who are separated by that sort of distance. So what we're looking at into the future, the ultimate goal of quantum key distribution network is long-distance, secure quantum communication with imperfect sources. So we want robustness in terms of the source and robustness in terms of the link. So some things to consider here are, the performance of your QKD systems. So currently, the secret key rate generation using classical systems is in order of 100 gigabytes per second, versus quantum systems which have the order of megabytes per second. So this is orders and orders of magnitude lower than a classical case. And we need to boost that. In terms of range, one can establish a classical key from here to the other side of the planet with no problems at 100 gigabytes per second, whereas currently, I think the best QKD systems, apart from the Chinese quantum satellite, which is, of course, insanely expensive, the ones that which are currently sitting on the ground can do a key distribution protocol for a range of several hundred kilometers. And range is a problem precisely because we can't amplify quantum states, right? So you can't simply measure and then boost like classical systems with quantum states. And lastly, we also need to consider cost and robustness of these systems. So they need to be compatible with being user-friendly and consumer-friendly, and they need to be robust against all different sorts of environmental noise. And so this is still currently a very active area of research, and we'll see what researchers do next to solve the problems. So that's it for the course. Thank you for your attention, and please feel free to email me any problems or questions that you have. And good luck with your exams and COVID and all the rest.